Beneath the steady rhythm of our daily lives, underneath our sprawling cities, lush forests, and endless prairies, there lies a realm of absolute darkness and profound silence. It is a world carved not by light or human hands, but by the relentless, quiet work of time, water, chemistry, and extreme pressure. We walk upon the crust of the earth assuming it is solid ground, but down below, the planet is hollowed out, laced with a labyrinth of subterranean passages, colossal vaulted chambers, and deep abyss-like shafts. Caves are among the most mysterious, ancient geological structures on Earth. They are silent archives of our planet's hidden history, preserving moments frozen in time from millions of years. To understand how a cave is born, we must first change how we think about the earth beneath us. Rock seems eternal, unyielding, and permanent. Yet, over vast geological timescales, even the hardest stone can be dissolved like a sugar cube in warm tea, hollowed out by torrential underground rivers, or carved apart by the searing heat of liquid magma. Caves come in many shapes, sizes, and origins, created by vastly different physical and chemical forces, from glowing crystal caverns deep in the earth to vast tunnels carved by glowing rivers of lava. To build a solution cave, nature requires three fundamental ingredients: soluble rock, water, and time. And that journey begins high up in the atmosphere with a single drop of rain. This is the story of how caves are created, step by step, across the immense tapestry of deep time. The dissolution realm, solution caves. The most common, massive, and intricate caves on Earth are known as solution caves. To build a solution cave, nature requires three fundamental ingredients: soluble rock, water, and time. Millions of years ago, vast, shallow oceans covered much of the Earth. In these warm, ancient seas, trillions of microscopic marine organisms lived, died, and sank to the seafloor. Their shells and skeletons, rich in calcium carbonate, accumulated in massive layers over eons. Under the crushing weight of overlaying sediment, these marine remains compressed and cemented into vast strata of sedimentary rock, primarily limestone and dolomite. Eventually, tectonic plates shifted. Continents collided, oceans retreated, and these massive beds of limestone were lifted above sea level, forming hills, plateaus, and mountains. But limestone has a secret vulnerability. While it is strong enough to support massive mountain ranges, it is easily dissolved by acid. And that is where the sky enters the equation. Every journey toward the creation of a solution cave begins high up in the atmosphere with a single drop of rain. As rain falls through the air, it absorbs small amounts of carbon dioxide gas. When the water hits the ground and seeps through the organic soil, it absorbs even more carbon dioxide produced by decaying leaves, roots, and bacteria. This simple chemical reaction transforms ordinary rainwater into a weak natural acid known as carbonic acid. It is mild, barely stronger than club soda, but to a bed of limestone, it is a slow, methodical weapon. As this mildly acidic rainwater trickles downward through the soil, it eventually encounters the solid limestone bedrock beneath. Bedrock is rarely seamless. It is fractured with vertical cracks, horizontal bedding planes, and fault lines caused by tectonic stress. The acidic water seeps into these microscopic fractures. Bit by bit, molecule by molecule, the carbonic acid reacts with the calcium carbonate in the rock, dissolving it and carrying it away in solution. What starts as a microscopic crack gradually widens into a hairline fissure. Over thousands of years, that fissure opens into a narrow pipe. Over tens of thousands of years, the pipe expands into a canyon-like conduit. Eventually, these underground conduits intersect the water table. the level below which the ground is completely saturated with water. Here, beneath the water table, the magic accelerates. Entire networks of underground streams and rivers flow through the submerged passages, constantly scouring the walls, carving out expansive networks of interconnected galleries. Then, a crucial shift occurs in the landscape above. Over hundreds of thousands of years, surface rivers on the outside world carved deeper valleys, causing the regional water table to drop. As the water table falls, the water that once filled the underground passages drains away, leaving behind vast, hollow, air-filled voids. For the first time in millions of years, the cave is empty, dark, and silent. But its creation is only half complete. The subterranean sculptor, Speleothems. Once a solution cave has been hollowed out, a second phase of creation begins. If the first phase was about destruction and removal, this second phase is about creation and decoration. This is the era of the Speleothems, the mineral deposits commonly known as stalactites and stalagmites. The process of carving the cave left behind a hollow space, but rainwater continues to fall on the surface world above. Raindrops seep through the soil, picking up carbon dioxide, becoming acidic, and dissolving limestone as they migrate downward toward the ceiling of the empty cave. When a drop of this mineral-rich water finally breaks through the ceiling into the air-filled chamber, it experiences a sudden shift in environment. The air inside the cave has a lower concentration of carbon dioxide than the water drop. To reach equilibrium, the water drop releases its dissolved carbon dioxide gas into the cave air, a process known as degassing. As the carbon dioxide leaves the water drop, its acidity drops and it can no longer hold the dissolved limestone. It's forced to deposit a tiny microscopic ring of pure mineral called calcite onto the ceiling. Drop after drop, year after year, century after century, this process repeats. A single drop leaves a tiny ring. The next drop travels through the center of that ring and leaves another at the tip. Over hundreds of years, this forms a delicate, hollow, glass-like tube hanging from the ceiling, known as a soda straw. Eventually, the center of the soda straw becomes blocked by mineral debris. Water is forced to run down the outside of the tube, depositing calcite along its length and thickening its base. Thus, a classic stalactite is born, hanging tight to the ceiling, tapering downward like a stone icicle. Not every drop of water stays on the ceiling long enough to deposit its mineral burden. Many drops fall, plunging down through the darkness to plash onto the cave floor below. As the water splashes, it loses more carbon dioxide and deposits its remaining calcite on the ground. Over centuries, these mineral splashes build upward from the floor, growing into thick, blunt spires known as stalagmites. Given enough time, tens or hundreds of thousands of years, a stalactite reaching down from above and a stalagmite reaching up from below will eventually meet in the middle. They fuse together in a slow-motion subterranean handshake, forming a solid stone pillar known as a column. Elsewhere, water trickling down a sloped wall creates delicate sheets of mineral deposits that look like frozen stone waterfalls or folded curtains of cave bacon. Where water pools on the ground, delicate calcite crystals grow into rimstone dams, trapping emerald green subterranean lakes. All of this happens at a glacial pace. On average, a stalactite grows only a fraction of a millimeter each year. A single stone column can represent 250,000 years of unbroken rainfall, chemical reactions, and silent mineral precipitation. Rivers of fire, lava tubes. While solution caves require millions of years of chemical weathering, another class of caves is born in a flash of heat and geological violence,
Lava tubes. Lava tubes do not form from water or acid, but from rivers of molten rock during volcanic eruptions. When a volcano erupts with low viscosity basaltic lava, similar to the eruptions seen in Hawaii or Iceland, rivers of glowing liquid rock at temperatures exceeding 2,000 degrees Fahrenheit pour down the flanks of the mountain. As this incandescent river flows downhill, its surface comes into direct contact with the cool, ambient air of the atmosphere. The top layer of the lava river cools rapidly, solidifying into a dark, crusty shell of solid rock. Beneath this newly formed roof, the main body of the lava continues to flow insulated by the stone ceiling above. Because the stone roof acts as a thermal blanket, the lava beneath remains intensely hot and liquid, continuing to melt and erode its channel deeper into the ground. Over time, the flow organizes itself into a highly efficient underground conduit, a fiery pipeline transporting molten rock miles away from the volcano's vent. Eventually, the eruption comes to an end. The supply of fresh lava from the volcanic vent stops. However, the lava already trapped inside the insulated tube continues to drain downhill under the pull of gravity. As the molten river empties out into the lower plains or the sea, it leaves behind a hollow, cylindrical tunnel beneath the surface. When a lava tube cools, it reveals a completely different world than a solution cave. There are no stalactites built of calcite here. Instead, you find smooth, glazed basalt walls, ripple marks on the floor showing where the last molten waves flowed, and tiny lava sickles, pendant-like stone drips formed as the molten ceiling dripped down just before solidifying forever. Lava tubes form in a matter of days or weeks, yet their structures can endure for tens of thousands of years. They are among the straightest, smoothest, and most structurally sound natural tunnels in existence. The forces of wind, sea, and ice. Beyond acid and lava, nature utilizes other raw physical forces to hollow out the Earth's margins. Along the coastlines of the world, where steep cliffs meet the relentless assault of the ocean, we find sea caves. Unlike solution caves, sea caves are not formed by chemical dissolution, but by raw mechanical power. Waves crashing against a sea cliff exert immense hydraulic pressure. As water slams into weak zones, fault lines, or soft rock layers in the cliff face, it traps and compresses air inside tiny cracks. The compressed air acts like a wedge, shattering the rock from the inside. At the same time, the ocean hurls sand, gravel, and boulders against the cliff face, acting like a giant natural sandblaster. Over centuries, this constant pounding hollows out deep-sea caverns that echo with the roar of the tides. High in the mountains or deep near the poles, a different kind of cave forms inside glacier ice caves. Here, summer meltwater on the surface of a glacier carves its way down into the ice sheet through vertical shafts called moulins. The water flows along the bedrock beneath the glacier, melting out translucent blue tunnels through the solid ice. These caves are dynamic and fleeting, sculpted in months, constantly shifting and destined to collapse as the glacier moves and melts. And in deep, dark places far below the surface, another strange chemical process creates some of the most surreal spaces on Earth: sulfuric acid caves. Unlike standard solution caves that dissolve from the top down via carbonic acid from rain, these caves are carved from the bottom up. Deep subterranean deposits of oil and natural gas release hydrogen sulfide gas. This gas rises through deep faults until it meets oxygen-rich groundwater near the surface, transforming itself into concentrated sulfuric acid. This violent acid literally eats away at limestone from below, dissolving massive caverns at breathtaking speeds and leaving behind thick crusts of snow-white gypsum crystals.
This is the mechanism that carved New Mexico's famous Carlsbad Caves and the stunning alien-like Lechugilia Cave.
Epilogue: Monuments of Deep Time. Whether carved over eons by a gentle acidic trickle of rainwater, melted out by rivers of volcanic fire, slammed open by the ocean's tides, or dissolved by subterranean acid, every cave is a testament to the dynamic forces shaping our planet. Caves are safe vaults of geological time. On the surface of the Earth, wind, rain, vegetation, and human activity constantly erase history. Mountains erode away, soil shifts, and ancient tracks are washed clean. But inside a cave, protected from the elements, time stands still. A footprint left in soft cave mud by an Ice Age human or a cave bear can remain perfectly preserved for 30,000 years. Mineral layers within a single stalactite hold precise chemical records of past climates, ancient rainfall patterns, and long-lost atmospheric compositions, acting as nature's climate clock. The next time you stand on open ground, remember, the world beneath your feet is not solid, silent stone. It is a living, breathing architecture of hollow chambers, winding passages, and hidden rivers. A dark, majestic wilderness sculpted by time itself, waiting silently in the dark.